Okay, everybody, let's begin Chapter 8. And this is kind of an interesting turning point for us because this, from Chapter 8 onward, is where you see the rest of this course feeling pretty darn similar. We're going to begin talking about confidence intervals. That's Chapter 8. And then Chapter 9, we'll get into hypothesis tests. And then we will be looking at a variety of other tests and intervals we can do. But what you'll notice is that what you'll see in Chapter 8 and 9 is that we sort of develop like a 5-step procedure, and that is basically repeated throughout the rest of the course. So truly, I feel like once you get your head wrapped around confidence intervals and hypothesis testing, that's the main theme of this course. Though it looks complicated at first, I think people always tend to, just feel comfortable with it after a little bit, and the rest of the course, in a way, is smooth sailing. Anecdotally, last semester when I taught these 3 stats classes, by and large, the third exam, the exam that was on Chapter 8 and 9 and 10, was the best exam for everybody. Everybody did better on that exam than exam 1 and 2. Okay, so, and it's not necessarily that the material got easier, it's just that it became very focused and very procedural, and it became easier to score well. And so I think you're going to have a good time with this once we just get our head wrapped around a few examples. So Chapter 8 is going to look at confidence intervals. Okay, confidence intervals is a very important idea in stats, it does 2 things. First of all, we're going to look at confidence intervals relating to a mean, okay, a population mean. So that's what 8.1 and 8.2 covers. And then 8.3 is going to cover finding confidence intervals to estimate a population proportion. So the whole idea here, just let me give a rough example. The whole idea is that you've got some sort of population, and we don't know what the distribution looks like. Who knows, okay? But somewhere in there, there's a mean, there's an average, there's a middle ground. Who knows what it is, but let's say there's the population mean. Well, what we kind of know is that if I were to take a sample from this population, and if I were to look at the distribution of my sample means, when I take a sample, maybe, let's say here's where the true mean is, that's where mu is, the population mean. Maybe my sample mean lands here. Okay, so it's close to the population mean, but it's not right on. Maybe, it could have been more left or more right or whatever. The idea is that when we sample and find a mean of a sample, we know that it's not going to be dead on equal to the population mean, but we hope it's close. So what we do is we construct an interval around that sample, and we say, I don't know exactly what this is. I'm not sure exactly what the population mean is, but I'm really damn sure that it lives in this window here. And that's the whole idea of a confidence interval. And the confidence level we get to choose. We get to choose how sure we want to be that the population mean lives within this little interval we create by first finding a sample. So that is the entire idea behind confidence intervals. We're going to take a sample and find the mean of the sample. We know that it's not the same as the population mean, but we hope it's pretty close. We would assume it's close if we're sampling correctly. And to hope that we scoop up the actual value of the mean, we build an interval around that sample mean. And we could say with a certain level of confidence, we feel pretty darn certain that the true population mean lives in that window somewhere. Okay, so this is what we're making now, these confidence intervals, these windows that hopefully capture the true actual mean that we're looking for, the mean of the population. Okay, so what we're going to rely on heavily from here on out is the central limit theorem, what we learned in Chapter 7, because remember, if you're going to calculate probability or analyze data, you really need to know what does the distribution look like. We don't always know that. And maybe we know it and the distribution is just really something ugly and not easy to analyze like this. That's not like a nice, smooth, symmetric, bell-shaped curve. But what we did learn is that when you sample from anything, right, central limit theorem tells us that when you sample from anything, as long as you do it right, that if you take a bunch of sample means that it's always going to be approximately normal, approximately nice and bell-shaped and symmetric. And that we can analyze very easily using z-tables or StatCrunch. So it doesn't matter what the original population, how its distribution was. As long as we obey the rules of central limit theorem, we can approximate this guy, the mean of the population, by analyzing our sample means here. And again, that's going to allow us to build our confidence interval. So if you recall what we learned in 7.1, the distribution of sample means, right, all this stuff, all the way all my sample means lay down, that's approximately normal as long as either the original population itself was normal to begin with, okay, which that sometimes happens. A lot of times we don't know those, so the other condition that we go by a lot is as long as our sample size is big enough, then we're going to have a distribution of sample means that's approximately normal. And if you remember, large enough for a mean, the requirement was that the sample size had to be at least 30. If the sample size was at least 30, then we feel really confident that our distribution of sample means will be normal and therefore easy to analyze. Now, if you also remember from the last section, 7.1, we learned that this distribution here will have a mean to it, and it's exactly the same as the mean of the population, right? So that's what they're telling us here. And we also know that this distribution has its own standard deviation that is not the same as the original population. Remember, the standard distribution of my sample means is this. The standard distribution of my sample means is the population standard deviation over the square root of n. But I need to know these two things. If you want to analyze this curve, you have to be able to tell StatCrunch what's the mean and what's the standard deviation in order to crank out the numbers. Or if you're trying to convert them to z-scores so you could use a z-table, you have to know that as well. Okay. So this first example is really going to have us do a confidence interval. We're going to then elaborate on it or get a little more specific with it, but that's what it has us doing. Okay, let's take a look. This says that suppose the students at a large college are currently taking a mean of 11.2 units with a standard deviation of 4.4 units. Okay, and they say right off the bat, note, the number of units taken are not normally distributed. So I don't know what this distribution looks like, okay, but they have some population. Again, I'm just going to make a funny shape. We know that the population mean, the mean number of units being taken by students at the college is 11.2. And we know that the population standard deviation is 4.4 units. Okay, so somehow they know that information. All right. So they're saying that 52 students at the school are randomly selected and asked how many units they're taking. So that's my sample size right there. We're taking a sample of 52 students and we survey them on how many units they're taking. Okay, here's the question. What is the probability that the sample of 52 students has a mean greater than 12 units? They are talking about a sample mean, the mean of a sample, right? So they're asking us to analyze X bar, okay? So it sometimes takes a few examples, you know, I feel like sometimes you have to kind of get the procedure down before you can really start to appreciate what's going on with these problems. But it's really powerful what we're going to be able to do here. By knowing a little bit of info about the population, we can find the likelihood of, if I were to grab 52 people, what's the likelihood that the average number of units taken among those 52 people is greater than 12? So before we walk in and ask those 52 people, I'm basically going to know the likelihood of getting that answer. Okay, and so again, this is also giving to us, it's presenting us with a shift from descriptive statistics to inferential statistics. So descriptive statistics is what we've been doing. Here's data, tell me about it. Here's data, tell me about it. You know, what's the mean? What's the standard deviation? Blah, blah, blah. What we're going to do now is we're going to start basically making more predictions, right, and making inferences based on some knowledge we have. So again, before I even ask these 52 people how many units they're taking, we're going to walk into that situation and know the likelihood of getting that answer. Okay. Well, again, I'm being asked to analyze sample means. Okay, so if I want to analyze the sample means, I mean, basically the question I'm trying to answer is this: what's the probability that the mean of this particular sample is greater than or equal to 12? Okay. We learned a long time ago, or a while ago, that if you want to calculate probability, you better know the distribution, right? Because depending on the distribution, the rules of the game, there's different ways to calculate probability. So how are these guys distributed? That's what we need to know, is what does that distribution look like? The distribution of sample means. Well, according to central limit theorem, as long as you take at least 30 in your sample size, then the distribution of sample means will be approximately normal. So since n is equal to 52, which is bigger than 30, by central limit theorem, the distribution of sample means is approximately normal. Well, that works out really well because I can do probability of a normal curve, either using a z-table or using StatCrunch. But I know it's, I know now it's not binomial or uniform because those all have different ways of doing probability. It's normal, okay? Simply by the fact that I took a large enough sample size. Okay. All right. Well, if I'm going to use StatCrunch or I'm going to use a z-table, I know that it's normal, all right, the distribution of all these x bars, but that's not entirely enough. What I need to know is what is the mean of all those things and what is the standard deviation of those things, right? Those two bits of information have to be used when finding your z-scores, or they have to be used, or you have to plug them into StatCrunch so that it knows, again, it needs to know, all right, is it a skinny normal curve? Is it a wide normal curve? You want me to find area under the curve, I can do it, but I have to know what type of what's the exact shape of that bell curve, all right? And this is what does it, the mean and standard deviation. So we learned that by central limit theorem, the mean of the sample means is the same as the population mean, which was 11.2. And we also learned by central limit theorem, and I'm using these formulas here, that the standard deviation of the sample means is the population standard deviation over the square root of n. So that would be 4.4 over the square root of 52, which if I put that in the calculator right, I got 0.61. So StatCrunch is going to need those two numbers from me in order to calculate this probability. Now, the probability, again, I'm looking for is this. I want the probability that a sample mean is greater than 12. I usually draw up a picture. You don't have to, but I usually kind of draw up a picture. Try and do a better one. We know the mean is 11.2. And I'm trying to find the likelihood of getting a sample mean greater than 12. So 12 is somewhere to the right, and I'm looking for that area. StatCrunch can do that for me right away. And so that's really how I'm going to do most of these. But I'll go ahead and do this one using a z-table just to kind of remind you that it can be done that way. It's just a little bit of a pain. So if you want to do this with a z-table, that's fine. You would just need to first convert to z-scores. For a z-table, hold on one sec. So remember, your z-score is always your data value minus the mean over your standard deviation, which for for this particular distribution, the sample means, my mean is 11.2 and my standard deviation is 0.61. Let's see what that comes out to. Oops. I get 1.31. So the equivalent picture here, or this picture, is equivalent to this picture where I'm working on a standard normal curve. If your standard normal curve, remember the mean is 0. So I've basically, again, I've standardized these scores so that my mean is 0, and that score of 12 translates into a z-score of 1.31. And I still want to be right at that number. Okay. Now again, here's where this is sort of a pain, because if you remember your z-tables, they only tell you left area. So when I look at the z-table and I look up this score, the area that it tells me is going to be this part right here. Okay. What I'm going to have to do is take 100% minus this part to be left with just the little black shaded region there. Let me find my z-table. Stats tables. I've got a positive z-score, and my z-score was 1.31. So 1.3 and 0.1, so right there. That is the area to the left of a z-score of 1.31. Okay, the area left there is 0.9049. All right, so let me go back to the notes. This area here is 0.9049. So if I want this area, the part that's shaded here in black, it would be 100%, or 1 minus the 0.9049 I do not want. So that is 0.0951, or 9.51%. So that's the probability I'm looking for. The probability that I'm going to ask these 52 students how many units they're taking, and the probability that the average answer I'm going to get is greater than 12, there's a 9.5% chance that's going to happen. So even before going in and talking to them, I know the likelihood of that happening. Let me go ahead and just show you that on StatCrunch. I've got it ready to go, how to do this calculation. With StatCrunch, again, you don't have to do this z-table conversion, which I do recommend you do quite a few times just to kind of get it down. But it certainly is easier on StatCrunch. I'm going to go to, what am I going to go to? Stat, Calculator, and I'm going to try this with my finger, not my pen, Calculators, and look for the distribution we're dealing with, which is normal. Okay, now they default to a standard normal curve, which I'm not. My curve has a mean of 11.2, right, because I'm trying to avoid having to convert to z-scores. And the standard deviation was 4.4, if I remember right. And I wanted the probability of getting a score greater than or equal to 12. And that does not look like what I got. So let me double check my numbers here. Hold on a second. Oh yeah, the population standard deviation was 4.4. For my distribution of sample means, it was 0.61. So I got to fix that, right? Because I'm supposed to be using these numbers, the mean of my sample means and the standard deviation of my sample means. So 0.61 is what it should be. So let's go back to StatCrunch. This standard deviation should be 0.61. Now let's see. There we go. 0.0948. So that's about 0.095, which is what I found, 9.5%. Okay, so we're right on there. Okay, but again, StatCrunch gives it a lot faster. We don't have to mess with any of this stuff. All right, now the second part is really, truly a confidence interval. They're not using those words, and they're not, they're kind of helping us do it along the way, but this right here is a confidence interval, what we're going to build. They say find the range of usual values for x bar. Consider the sample means within two standard deviations to be usual. So again, if you're going to go ask these 52 people how many units they're taking, what they're asking us to do is they're asking us to create a window that will capture all the answers that we would consider usual. And remember, earlier we learned that we considered anything more than 2 standard deviations from the mean to be unusual. Okay, so we're talking about finding things within 2 standard deviations of the mean. So really I'm going to have a window here where I'm going to take my sample mean, right, or the mean of my sample means, and I'm going to go 2 standard deviations to the right, 2 standard deviations of my sample mean to the right, and I'm going to go 2 to the left, and that window is going to contain all the answers, all the number of units that we would consider to be not abnormal, right? Because they're not beyond 2 standard deviations. This is absolutely a confidence interval. In fact, the only thing that's going to change with a confidence interval is you don't have to use the number 2. You could use any number you want. That is the confidence level, and that determines how wide or narrow your window is here. But that's all that we're going to add to this, is we're going to say, well, what if I don't want 2? What if I want something different? How do I deal with that? So, again, they give me the format here. I'm going to take the mean of my sample means, and I'm going to add and subtract 2 standard deviations to that to create this window that captures everybody that we would consider normal. All the answers from these 52 folks that we would consider normal and not unusual. Well, the mean of my sample means is 11.2. The standard deviation of my sample means we found up here, that's 0.61. Okay. So again, what this does is this gives me a little window that we create. All right. Down here would be 11.2 minus 2 standard deviations. And up here would be 11.2 plus 2 standard deviations. Right in the middle of that would be my mean, 11.2. If I put these in the calculator, right, this is 9.98 and this is 12.42. All right, and so this gives me a little window here, right, from 9.98 to 12.42. That window, we would expect those numbers to contain all the normal answers. So if I ask these 52 people how many units they're taking, and I end up with an average of 13, I would say that's weird. That's unusual, because that's beyond 2 standard deviations from the mean, right? 13 would be somewhere around here. So it would be outside of 2 standard deviations. I would consider that an unusual answer. This window right here would be where I would expect all my typical answers to be, between 9.98 and 12.42. That's what we would expect a sample mean, or our mean, to come out to when asking these 52 people how many units they're taking. Okay. All right, so let's go on to the next page. Okay, so here's what we're really trying to do with some of this stuff, is we're always interested in learning about a population. And again, maybe we have no idea what the population distribution looks like, and maybe I don't know what the mean is, but I want to know that mean. Let's say I want to know what that population mean is. Okay. Well, what we're going to do is we're going to create a confidence interval to guess it. We're going to take a sample, and again, my sample mean's not going to be right on it, but it's going to hopefully be close. And around the sample mean, we're going to create a window, a confidence interval. And based on how confident we want to be is what's going to determine how wide the window is. But basically, we are hoping that the true mean lives somewhere in that window. So that way we're going to be able to say, well, I can't tell you exactly what the average value of that population is, whatever the heck we're talking about, but I can tell you very confidently that it's between these two numbers. That tells us a lot about the population mean, and that's generally all we need to know. Okay. So there's two types of estimators that we're going to talk about. There's point estimators and there's interval estimators. A point estimator is a single value estimate for parameter. So this x bar was like my point estimator, okay? The sample mean there, right? The average of my sample was a single estimate at the population mean. An interval estimate is a range of good estimates for the parameter. And this generally does a better job of capturing those. So this, here they just said if you take x bar and go 2 standard deviations either side for it, you're pretty darn likely to capture the population mean there, okay? So again, all we're going to do is we're going to fine-tune this idea a little bit and say you don't always have to use 2 standard deviations. You could use more, you could use less. That's based on how confident you want to be. But again, this idea is that a point is not going to do the best job estimating the population parameter. But if you start with that point and you build a window around it, that's probably really likely to capture that population parameter. That's the entire idea of a confidence interval. Okay, so here we go. Confidence intervals, you'll see us refer to them as CI a lot, okay? So a confidence interval is an interval estimate, all right? It's exactly this idea right here for estimating some parameter. Now, when we're doing a confidence interval, we're going to see that there's officially going to be a procedure to follow, but that's coming in a little bit. Really, there's 2 main things we need to talk about or to provide. You have to provide the range of values that you think the parameter falls under. Okay, so this would be like my interval estimate. Just like on the last problem we did, the interval we came up with was what, 9.9 to 12, something like that. That was the interval that we felt pretty confident our sample mean would end up in. This is a similar idea, we're just using it as a different idea. We're trying to make a prediction about a population parameter that we don't know yet. So anyways, I need to tell them what this estimate is. This is like the green window or interval that I've got over here on the right. And then the other thing we need to talk about is how confident are we? What's our confidence level? We're going to see that the confidence level actually determines, again, how wide or narrow that window is, and it really tells us sort of how much weight we can put behind our findings. Okay. Now, a confidence level, okay, is actually a success rate. And this could be a little bit confusing because we're going to say like, you know, we're going to use like the common confidence levels are like 90, 95, and 99%. We could use any level we want, but those are common. So it gets a little confusing because sometimes people think that, oh, when I have a 95% confidence level, they think, well, there's a 95% chance that my true answer is going to be there, or that when I take this sample and find this interval, there's a 95% chance that it captured the true value. That's not really the way to think about it. The way to think about it is, okay, I've got some funky population, and there is a true mean. That's what I'm trying to find. And if I create a confidence interval, sometimes I'm going to get it and sometimes I'm not. So sometimes maybe my sample mean is close enough to where I get a sample mean, and when I construct my window around it, boom, I captured it, right? Wouldn't this guy fall within that window? However, sometimes my sample mean can be so far away, maybe just it was a weird sample and my sample mean was here, So when I construct the same window, do you see I missed it, right? Like mu didn't land in that window. I missed it. So sometimes you're going to hit it, sometimes you're going to miss it. All right, your confidence interval will not always capture the true population parameter, but a lot of times it will. And that's what the confidence level is. It's the success rate. It's how many times it happened. So if you've got a 90% confidence level, what that means is that if you were to do this thing that I just did 100 times, okay, that 90 of those times we would capture it. 10 of those times you would miss. Okay. Again, 90% of the time that you make an interval, you will be capturing the true value. 10% of the time, you will not be capturing the value because maybe your sample mean was just too far left or right, so that even when you construct the window, you're still missing the population mean. Okay, so be sure to think of it as a success rate. It's not like it's telling you the likelihood of you capturing it on the next go. Let's see, I'm going to skip over this part in the notes. So here is the general form of a confidence interval. It always starts with a statistic. This is your point estimate. We're either going to be looking at a sample mean or a sample proportion. That's an 8.3 that will do those. For now, we're just going to worry about sample means. And then to that, you're going to add and subtract this idea, your critical value times the standard deviation of the statistic. And we were doing this. We were adding 2 standard deviations. In the last 2 problems, didn't we add and subtract 2 standard deviations from the mean? Well, like I said, it doesn't always have to be 2. You get to decide that. That is known as your critical value. Okay, and then of course we have the standard deviation of whatever we're dealing with, whether it be the sample mean or sample proportion. Now this together is known as the margin of error. The margin of error is basically the width of the window, right? Or it's how far you go left or right from your point estimate, okay? So this right here would be my margin of error. Same as this thing, right? Again, it's how far you go left or right from your point estimate, from your statistic. If we want to use some stats notation, my statistic is, again, for now, we're looking at sample means. So that would be my first guess. If I'm trying to guess the population mean, I would start by guessing or looking for a sample mean. And then I've got a critical value, which is going to be a z-score, and they label it z-star just to kind of tell you that they're talking about a critical value that's being used in a confidence interval or a hypothesis test. So that's the reason for the little star there. And then the standard deviation, well, we learned, remember, that according to central limit theorem, that the standard deviation for your sample means is the population standard deviation over the square root of n. So if you're investigating the population mean, you're using the sample mean and you're using the standard deviation of your sample means. Okay? And again, this guy is based on our confidence. So we'll take a look at just at how to find that, I think, on the next page. Okay, this next page is devoted to finding that critical z-score. Okay, that's all this page is dealing with, is finding that critical score. So here's the idea, and here's what they're trying to show in this table. I'm going to try and draw it to the side. But let's say that my level of confidence is 95%. Okay, so if my confidence level is 95%, what that means is that on a normal curve, I am trying to, well, for one, I'm going to block off 95% of the data. So I'm going to say, okay, there's 95% of my data. My critical z-score is going to be these numbers right here, right? Now, by symmetry, they're going to be the same. Whatever z-score this is that cuts off, oh, well, let me just add real quick. Let me see. If this is 95% here in the middle, then doesn't this leftover and this leftover make up 5%, right? And so that's what they're getting at there, is that the leftovers here and here make up 5%. If you want to find the z-score that obtains that particular area there, remember the way our z-tables work basically is I would just look for the area left of this particular number. Or if you were to take this blue shaded area and cut it in half, that's what they're doing here, we would see that this area is 0.025 and this area is 0.025. And again, the area inside is 0.95. They all add up to 1. Okay. So again, I hope that makes sense, that if you've got 95% cutoff in the middle, that together the two blue parts need to add up to 5%. So individually, they're 2.5% each. Okay. So your critical z-score is going to be the z-score that cuts off the lower 2.5% or the upper 2.5%. And by symmetry, these are going to be the same numbers. They're just going to be, one's going to be negative and one's going to be positive. And because in our interval we're adding and subtracting these numbers, we don't really bother with the negative sign, although we usually end up finding this one because our z-tables work this way. They tell us left area. But when you go consult the z-table, you're going to get a negative z-score. You'll see that our z-star value we use ends up just being the positive version of that. And again, because you're going to be adding and subtracting that amount, so it doesn't really matter if you have a positive or a negative. It's going to work out the same either way. Or you can consult StatCrunch and they'll help you find these numbers. Okay. So down below they have us doing some practice. Oh, you. I'm sorry about that. My cat's so annoying. It literally just bumped my computer and turned it off. So I hope that I'll have to look back and make sure that's smooth and that everything got recorded. Okay, so I think I was saying that down below they're going to have us find some critical z-scores. And again, I know that you might be feeling like, I hope you're not feeling like, what the hell has Ben talking about, that this feels way over my head. If you can just muscle through and make it to where we do some full-blown confidence intervals, I swear by the time you've done your third, fourth, or fifth one, you've got the pattern down, the rhythm down, and you can do them all the way from here till the end of class. Okay, because like I said, it's almost like from now on, we're not changing much on you at all. Like you learn how to do this and you just do it over and over and over and over again. Okay, so truly, may not feel like it now, but truly we are approaching the easier part of the class. All right. Okay. I mentioned earlier that there are some very common confidence levels that we use, and so those, like I said, would be 90, 95, and 99%. Alpha, this alpha represents this area left in the tails here. All right, so that's what they're talking about there. And these are the critical z-scores that we would find when we are looking them up in a z-table, and they call them alpha over 2, z sub alpha over 2. That's another symbol that some textbooks use, because again, if you're looking at say you want 90% confidence, that means the middle area is 90%. That means the two of these areas combined make up 10%, which means that just one area, which is all you would need to look up on a z-table, is just one, that right there is going to contain 5%, right? That is alpha over 2 to get 5%, okay? Anyways, so if you were to look up on a z-table, this would have a z-score here of negative 1.645, and on here would be the positive 1.645, right? I'm just going off what they're telling me here. Again, we do not worry about the negative one. We just usually that's the one we find, again, because of how our z-tables work, but we just take the positive value because we're adding and subtracting them. So let's just find some critical z-scores on this page, and then the next page, I think, actually has us build a confidence interval, okay? So here they just want us to find the critical values. Suppose you're trying to make a 98% confidence interval. Okay, so they just want us to find the z-score we should use, the critical z-score. All right, 98% confidence interval means I'm blocking off 0.98 of the middle, right? 98% of the middle is getting blocked off. I want to know what are the z-scores here that make that happen. Well, if it's 0.98, if it's 98% in the middle, doesn't that mean that there's 2% combined in both of these arms? 2%, right? Which means they would each hold 1%. Right? Again, 98% in the middle means the combined value of the two blue areas must be 2% because it's all got to add to 100. So if I cut that in half, I get 1% per blue area. So all I'm going to do is, because my z-tables focus on left area, I'm just going to focus on that, consult my z-table, and see what it is. The difference here is I'm looking up, I know the area, and I'm trying to find the z-score. So let me go to my z-table. Okay. All right, so this is all some old stuff. Let me clear this out. All right, so again, what I've got now is I've got an area that I'm trying to look at. I want the area left of this z-score to be 0.01. I'm trying to find what z-score makes that happen. I know that I should be reading the negative z-score values because if you go back to my picture, I've got a z-score to the right of the mean, and I'm looking at the one to the left of the mean. So these are left of the mean, so they will be negative z-scores. Okay. So I just need to find where is an area of 0.01. So let me look down here in the table. There's close. Probably right on. Okay, it's like right in between there, isn't it? There's 0.01, 02, and there's 0.099. So it's sort of right in between those. It's right in between those where you'd expect to see 0.01. So I'm just going to go right in between those numbers. So to me, what I've got here is I've got a z-score of negative 2.325. Negative 2.325. That right there is blocking off 1% to the left. Okay, and if I wanted to, if I were to try and figure it out, to leave 1% to the right would be positive 2.325. Okay, now let me go back to my notes for my z. Hold on a second here. Is this the page I'm on? Yeah. For my critical z value, again, I don't worry about a negative, so I'm just going to say the z value I would use would be 2.325. I think that was it. I just forgot. Let me just leave it at that. I better double check. 2. That's the positive table. Apparently I clicked on something else, but 2.325, yeah. Okay. Let me go back. And this is definitely something I want to do with you guys in class, or little virtual classes, work these out. Let's try and find this one. So here I've got I'm trying to do an 80% confidence interval. So I'm trying to block off the middle 80%. Doesn't that leave a total of 20% combined? Well, since there's two arms, you cut it. Whoa, hold on, one note crashed on me. Let me put it back up. 80% confidence interval. I'm trying to leave 80% in the middle. That means 20% left combined between those two arms, total of 10% each arm. Okay. So what I would do is if I want to just, oh, come on. I might have to turn this off and restart it, guys. Okay, I'm just going to not highlight it or something. Maybe I'm just pissing it off. Okay, so I hope that makes sense that I would have 10% in each of those arms, 80% in the middle, and we're looking for the z-score that pulls that off. Doesn't matter if you find this one or this one, but if you're using a z-table, you're going to look here because, again, z-tables tell you left area. Okay, but I could also do this with StatCrunch, so let's just do that. If I think about it, if I go to StatCrunch, I'm just going to try and find a standard normal curve that has 10% area to the left. So let me just close this and somehow figure out how to scroll up. I'm going to go to Stat, Calculators. I'm going to try it. Normal. And I've got my standard normal curve in because I've got a mean of 0 and a standard deviation of 1. And I do want left area, but I don't want what I'm trying to do is I want to type in the area here. I'm looking for an area of 0.1. Will that work? No. If I delete it, it will. 0.1 is the area I'm looking for. Okay. And notice it tells me negative 1.28 would be the z-score that would do that. If you want to leave 10% area to the left, the z-score is negative 1.28. So the critical z-value I would use, 1.28. Again, I don't have to worry about taking the minus sign because I'm going to add and subtract that amount or that many standard deviations to my sample mean. For a 99.5% confidence interval, I'm trying to block off 0.995. 99.5% is what I'm trying to block off on the middle, which means the leftovers make up the last 0.5%. So between the two of these together, they make up 0.005. If you cut that in half, this one arm is 0.0025 and this is 0.0025. So I've got two options. Either consult StatCrunch and look for that area on your negative z-table. I'm sorry, if you're doing a z-table, or just go into StatCrunch and type in that area. So I'm going to do that. Go back to StatCrunch. This time I want the area left of my curve to be 0.0025. There's the area. There's the z-score that gets it done, negative 2.8. Okay. And then the last one I'm just going to cheat because they have the answer here. 90% confidence interval means you're trying to block off 90%. Means these last two arms together would be 5%. Because 5 and 5 makes 10 on top of 90 gives us 100. If you were to consult your z-table or StatCrunch, you would see that the z-score you should end up using, or this z-score here, would be negative 1.645. So the critical z-score I would use would just be positive 1.645. We're going to use those so frequently, especially these two, that I think you will naturally have them memorized just, after you've used them 4 or 5 times. But I would remember those or write those down because it'll save you time from having to do this process. Okay. All right. Let's take a look at the next page where we're actually going to do an example. Okay. So let's take a look at this example and where they actually want us to calculate a confidence interval. It says, suppose we wish to estimate the average math SAT score for students at a local high school. So they want us to estimate the average math SAT score. So we're trying to estimate something about the population mean. The population being these high school students, and we want to know the mean SAT score. Okay. Again, we can get a good idea by taking a sample and finding out how the sample of students did on the SATs, or as far as how their math score was on the SATs. But we know, and again, maybe this SAT scores, who knows what the distribution looks like, but there is some average math score. We know that if I sample, that maybe my sample will be a little under or a little above the true mean. So again, what we're going to do is we're going to say, well, let's take our sample and let's make a window around it, and let's hope or feel confident that our window scooped up the true mean math SAT score at this high school. So they're saying that they randomly select 40 of the 850 seniors who took the SAT at the high school, and we find that of those 40, the mean score of those 40 students was 438. That right there is my estimate, 438. Now I drew it below the mean. I don't really know, so I just guessed. But we're going to take that number, we're going to take 438, and we're going to add some standard deviations to the right, subtract some standard deviations to the left, and we're going to hopefully scoop up the true mean that we're trying to estimate. Okay, that's what we're doing here. It says, suppose we know that the standard deviation of the population, so that's sigma, is 105, which is a bizarre thing to know, and we'll talk about that in just a second, because if you think about it, it's really weird that we would not know the population mean, but somehow we know the population standard deviation. You know, that's like me saying, I don't know how many hours on average I sleep a night, but I know the standard deviation is 3.1 hours. Like, that's weird. Okay, so and that's leading into what we're going to talk about next. But right now, let's ignore it. Let's build this confidence interval. They ask us to build a 95% confidence interval to estimate the mean math SAT score for the entire senior class at this high school. So again, they're saying build that interval. Take that starting point of 438, that point estimate, add some standard deviations left, take away standard deviations. I think I said that all backwards, but we're going to add standard deviations and subtract standard deviations. How many standard deviations should we add and subtract? Well, we're not just doing necessarily 2, okay? We're doing it based on a 95% confidence interval. So what we know is basically that my sample means, well, actually I drew them to be normal. Do we know they're normal? Are the sample means normally distributed? The answer, I'm hoping you're saying, is yes. How come? Right? Because we know that if I do a bunch of sample means under the right conditions, yep, they're going to be normally distributed. Did we meet those conditions? We did, because our sample size is big enough, right? Since n is 40, which is bigger than 30, that's all we got to do is take at least 30 folks, and then our sample means will be normally distributed. Okay, so I know my sample means are normally distributed, and I know that my confidence interval needs to block off, or I'm interested in finding a z-score that's going to block off 95% of the data. Again, this is how many standard deviations I'm going to move left or right of my sample mean. I need to know, what is this critical z-score here? Well, you could do it exactly how we'd been doing it, okay? You can calculate that if this is 95%, then together these are 5%, so they're each 2.5%. And you can consult the z-table, or you can consult StatCrunch to figure out that critical z-score, or 95% is a popular one. You could just learn and read on the table on the previous page that z-score is 1.96. So let me just write a few things down that we know here. We know that my sample mean, my starting point estimate is 438. My critical z-score is going to be 1.96. And the standard deviation of my sample means is the population standard deviation over the square root of n. Remember, because we're normally distributed, and that's according to central limit theorem. So it's going to be 400, no, the population standard deviation was 105 over the square root of 40, which I didn't figure out yet. Let's see. $16.6. So here's why I'm writing all this stuff down, okay? Because if you remember the general form of your confidence interval, all right, the general form is that I'm going to take my estimate, my point estimate, which in this case is the sample mean, and then you're going to add and subtract your margin of error. All right, which my margin of error is the number of standard deviations you want to move left or right of your mean. So it's your critical number times your standard deviation. Okay, so that's why I had to write down my point estimate, my critical number, my standard deviation. Now I'm just going to plug those in. My point estimate was 438, right? So that's my starting value. And then I'm going to add and subtract to that a bunch of standard deviations. How many? 1.96 of them, because that's the critical number that correlates or corresponds to a 95% confidence level. What is the standard deviation? We said that the standard deviation for these sample means was 16.6. Okay? So if I take 438 and I add that, what I end up getting is 470.54. If I take 438 and I subtract that number, what I get down here is 405.46. Okay. All right. So you see this written two ways. Sometimes this is written in interval notation. So they'd say 405.46 up to 470.54, or inequality notation. The population mean is in between those two numbers. But the real important thing to do is that we can interpret them. Okay, so again, let me just kind of jump back up to this picture I drew earlier. We want to know this population mean. We figure it out by finding a sample mean and adding standard deviations. And based on our level of confidence, we added 1.96 standard deviations to the right, subtracted to the left, and we got these values, 405 and 470 something. And we're pretty darn confident that we captured the mean in there. Again, it's not guaranteed. It just means that if we were to repeat this procedure 100 times, if we were to sample 40 students from the school 100 times, that 95 of those times we would scoop up the correct answer. 5 of the times we'd miss, 95 of the times we would get it. So we feel pretty darn good that we got it here. So we should always state a conclusion. And you can always just write this conclusion exactly the same. We are 95% confident that the true math SAT score, or whatever it is you're looking for, is between 405.46 and 470.54. for the entire high school, we are very confident that the average math SAT score is between those two numbers. And so what we were able to do is we were able to make a very strong prediction about the population mean by only starting with our sample mean, right? Our sample mean allowed us to get a good estimate of the population mean to a high level of confidence. Okay, now let's get back to this idea here that I mentioned, that it's weird that we did not know the population mean, but we somehow knew the population standard deviation. Okay, again, that's just kind of a weird thing. Generally, you wouldn't know this if you didn't know the sample mean. Okay, like I said, I used the sleep analogy. It's weird to say that, I don't know on average how many hours a night I sleep, but I do know that the standard deviation is 1.2. Like, that's bizarre. You'd be more likely to know the mean. So there's an issue with this, and there's a way to get around it. And so that's what this is kind of saying. It's like, what's up with that? How come you know the mean but not the, or sorry, you don't know the mean but you do know the standard deviation? That's probably not likely to happen. There's times where it could happen, but most likely that's not going to be the case. So this actually tells us about a new type of distribution. It's called the student t-distribution. And this is actually thanks to Guinness Beer. There was a quality control guy at the Guinness factory who was trying to, find how much beer was being bottled or was in a bottle. And so he was trying to estimate a mean, okay, the population mean from a sample mean, but he didn't know the population standard deviation. And so he said, well, instead I'm going to use the sample standard deviation, S. Okay, instead of using the population standard deviation here to calculate my critical z-score, I'm going to use the sample standard deviation to calculate my critical z-score. It turns out that when you switch from using population standard deviation to sample standard deviation to calculate your critical score, your critical number that you're going to tell you how many standard deviations to go left or right, turns out that that's no longer normal. It's close, but it's not normally distributed. It actually follows a t-distribution, okay? All that means for us is that we consult a different table. Okay, so when you're dealing with the t-distribution, you're just not going to look at a z-table. You're going to look at a t-table to find your critical scores. But otherwise, you're going to do everything exactly the same. The reason this is known as the student t-distribution is I should have looked up the guy's name. I don't recall the name of the guy that came up with this, but he was under contract basically not to publish any findings while an employee of the factory. He wanted to share his findings, so he just published it under the name student. Okay, and so it's known as the student t-distribution. Okay, so this we would, instead of z, we would call it t. It's a t-score, okay, not a z-score, a t-score. All right, so on the next page, they talk about a t-distribution, okay? So again, this is very closely related to a z-score, because isn't a z-score, remember, it's your data value minus the mean over the standard deviation. Now, again, we're talking about the distribution of sample means, so my data value is going to be a sample mean. All right, the mean is the mean of the population, and the standard deviation, remember, this is how we find standard deviation for these guys, according to the central limit theorem, except we're supposed to be using this. And again, we generally will not know that. Right? If you don't know the population mean, then you probably don't know the population standard deviation, and so we would approximate it using the sample standard deviation. Now, the difference between these guys, so if you've got a normal curve, it's bell-shaped, right? This is normal. T-distribution is similar, it's just wider. So it's still symmetric and unimodal, but it has wider tails. And what we've kind of hinted at or talked about earlier is that when you have wider tails, you've got more spread, all right? And so there's more variation. It's not quite as precise. And another thing that's different is we'll learn that this curve right here is based on what we call the degrees of freedom, which is really tied to the sample size. The sample size is what's going to determine how wide this curve is. And again, when it comes to finding probability, it's not hard. You consult a table, you consult StatCrunch, but you have to be able to tell the table or StatCrunch how wide this particular curve is in order for them to give you an accurate answer. Okay. So the degrees of freedom, we always need to keep track of that. It turns out that it's just it's your sample size minus 1. It's 1 less than your sample size is what we classify as the degrees of freedom. And we usually denote that with subscript right here. So if something follows a t-distribution, they usually write the degrees of freedom down at the bottom there, like a little subscript, okay? So if we want to build a one sample t interval, what we did earlier was a one sample z interval, but if you want to do a one sample t interval, the confidence interval is exactly the same format. You take your point statistic, your point estimator, and then you're going to add and subtract your critical value times the standard deviation of that particular point estimator. So the difference here is that my standard deviation is a little different in that we're using, again, the sample standard deviation because we probably don't know the population standard deviation. And I'm not using a z-score, I'm using a t-score, okay? Because, again, of this exact reason, because I'm approximating the population standard deviation with the one we find from our sample. Now, to find, again, the t-score, you do the same thing. I would draw a picture to help just kind of so you know which side of the curve you're looking at and to get your numbers right. But you find that critical t-value the same way you do the z-value, either with StatCrunch or a table. Now, the table would just be a t-distribution table, which is posted on Canvas. It's in the file stat tables where you find the z-tables. It's just a few more down to the bottom. Okay, I've changed my mind. I'm a little worn out from this. This is going to be part 1 of the video. I'm going to stop here and I will come back tomorrow and finish part 2 where we'll cover the last 3 pages of the notes, okay? All right.